All right, in chapter 4, we're going to continue our study of descriptive statistics. We said we will look at stem and leaf displays, percentiles, and box plots. We will hopefully end with a discussion and review of all the skewness. Ready? All right, turn over to page 96. Load it up. And let's start with the first technique that we're going to review, and that is a stem and leaf display. What advantage are we going to have using stem and leaf? The advantage is it's going to organize the data with a frequency distribution that will create a visual picture of the shape of the distribution. So here we recall the frequency distribution, but now we've all heard a picture's worth 1,000 words. What we're going to start doing here is creating these pictures where at quick glance we're going to be able to form the basis. We're going to be able to form some conclusion. Now, obviously, if we wanted to go deeper and test that conclusion, we would go back into some of the measures we've already looked at. Disadvantages of a stem and leaf are what?
We will use exact identity of each value. We're not sure how the values within each class.
All right, the two advantages. The exact identity of each value is lost. And it is difficult to tell how the values within each class are distributed. All right. That's why we use the stem and leaf. Okay, so on page 97, let's start. Remember, we don't want to lose. So let's stand. Okay, listed in table 4.1 is the number of 30-second radio advertising spots purchased by each of the 45 members of the Greater Buffalo automobile dealers. Organize the data into a stem and leaf display, and around what values do the numbers of advertising spots tend to cluster? What is the fewest number of spots purchased by a dealer? All right, first thing, we're going to create the stems. And the leaves. So what is the smallest number of spots purchased? The first thing you would want to do is organize the data from minimum to maximum values.
88.
So the smallest value is 88. So for the stem, we're going to use that first value, the 8, and the leaf is the other 8. Now, do we have any other value? What's the largest value?
I see 156.
All right, so the largest value we're going to create is the 156. All right, so let's go through here. 88. See another value in the 80 range.
89.
89. Anything else? Next, create a stem for our 9. What do we have in the 9s?
3, a 5, a 6.
5, 6.
So we say a 6, a 3,
4.
Next, we'll create a stem for the 10. So now we're looking at anything within the 100 range.
8.
So we see first we observe 108. Let's look at our 11s. First, I see a 117. I see 113. What's next? 12. 112. 117. 112. 111.
19.
119.
18.
118.
20.
And 113. Create a stem for our 12.
7.
So 127, 125,
7.
127 again,
5.
120. So I'll look at that. 125, 125, 20, 124. For 13, we have 139, 135, 132, 139, 134, 136, 138. Stem for 114.
148.
148.
142.
142.
143.
143. For the 150,
This is going to have
a 5 and a 5. Remember, we are asked to, around what values do the number of advertising spots tend to cluster?
around 110, between 110 and 120.
Yes, definitely, our values are going to, we're maxed here, we kind of cluster into this range. You can draw conclusions that quickly 2 dealers purchase less than what? 90 slots. Now compare this, remember when we had that frequency distribution, we just had data up there. Well, now I can organize this data and immediately start drawing conclusions from first look.
Spots 20 Melito bias.
It's too dang many.
Even that whole 50 category down there, huh?
He's up there like a 200, but yeah, he's insane.
Advertising works. I always say they don't purchase that airtime. I assume they don't purchase it without seeing some type of result. All right, flip over to page 102. Now we're going to continue our look on the measures of position. The last video showed and solved for standard deviation. That's still going to be your most widely used measurement of dispersion. The most widely used measurement of position. However, there are other ways to describe the variation around the mean. Three measures include the quartiles, the deciles, and the percentiles. When I talk about quartiles, how many values do you think I'm going to divide the observations in? 4. Deciles. 10. Percentiles. 100. So let's go over here. First, we'll look at percentile. And we're going to use the formula on page 102, which says that the location of a percentile, so the location of the percentile is equal to what? What's the N referencing?
Sample.
What's the P? What's the P referencing?
What's that now?
P is going to reference your desired percentile. All right, so let's look at broker commissions, bottom of page 102. It says listed below are the commissions earned last month by a sample of 15 brokers. You can tell this book's already Smith Barney name is more than an afterthought in most circles. So we're going to say listed below are the commissions earned last month by a sample of 15 brokers at Morgan Stanley. Oakland, California office. Morgan Stanley is an investment company with offices located throughout the world. Bless you. All right, so first, locate what we're asked for. Locate the median, the first quartile, and the third quartile for the commissions earned. Top of page 103, what's the first step that we're doing?
Sort the data from the smallest division to the largest.
All right, so let's look at these numbers. Give them to me after we've sorted them.
Oh, the smallest? Okay.
1,406.
460.
Yeah, 14 to 60. Then there's a 20.
Yeah, 1460.
All right, so 1460, 1471,
177, 1721, 1758, 1787, 1940,
194 what?
0.
0.
And then,
2038, 2047, 2054, 2097, 2205,
22 what?
05, 2287,
What's that? Is that a number, 2205?
yeah, that's it. 2287.
2205.
I've never heard of a number of 2205.
2,205.
For those of you who've had me in class before, O is not a number. Show that education when you speak to us here.
2287.
2205, and then what?
2287.
2,287.
2311.
2311.
2406.
2406. It never gets old for my Okay, so first step, which said we were going to organize them from smallest to the largest commission. And now it's asking us to locate the median. All right, so how are we going to locate the median? What percentile would equal the median?
50.
It would equal 50. Look in your book. Tell me how they're going to solve this.
You don't have 50 for that P, right?
Excuse me?
So that P's got to equal 50 up there at the top.
Correct. That's going to be my desired percentile. First, we said we would solve for the median. How many values are up there?
15. So 2038 is your median.
So 15 plus 1. And then what's my desired percentile? 50. 50 divided by 100. So what is that value?
8.
Now it says locate the first quartile. So the first quartile. What's going to be my desired percentile when I talk about the first quartile? So the location of the 21st percentile is what? Same number of values.
25. So 4.
And lastly, it says to locate the third quartile for the commission's earnings. So what's going to be my third quartile? Remember, still using the same 15 observations. Any questions?
So the number,
No. He was gonna be like, oh, I wrote that.
I thought you were gonna say so. All right.
so the 50 is a given number when they say the desired percent.
We used the 50 because we were calculating the median. Median's always in the middle, so it's going to be the 50th percentile.
And then 75, 75.
First quartile is going to be up to 25. The median is going to be 50. Third quartile is 75. Fourth quartile goes all the way up to the end. All right, let's look at a box plot. Someone tell me what is a box plot?
Graphical display based on quartiles that helps us picture a set of data.
Graphical display based on quartiles that helps us picture a set of data. And to construct a box plot, we're going to need to know some observations. What is it we're going to need to know?
Minimum
The
value,
minimum value.
first quartile,
First quartile.
the median,
The median.
third quartile,
Third
and the
quartile.
maximum.
And the maximum value. All right, so let's look at an example with Alexander's Pizza. So on page 106 in your textbook. And it says Alexander's Pizza offers free delivery within 15 miles. Alex is the owner, and he wants some information on the time it takes for delivery. How long does a typical delivery take? Within what range of times will most deliveries be completed? And do you think companies such as Domino's, made famous by guaranteeing pizza be delivered within 30 minutes or less, would have used something like this? So now Alex has a sample of 20 deliveries, and he has determined the following. The minimum value is what? 13. So the minimum time, so we have a sample of 20. And the minimum time it took to deliver was 13 minutes. The first quartile was 15. Was the median. 18 minutes.
22,
22. What was the maximum amount?
30.
30. Alex may have been the first person that done it. All right, so the first step, we're going to develop a box plot for the delivery time, and then I'll ask what conclusions can we make. And what is step 1? The first step is to create an appropriate scaling along the horizontal axis. So, how long do I know that my axis has to be?
13 to 30.
We know it has to at least go beyond these two numbers. So the book is going to start us at 12 and run out to 32. Okay, now where is our median? He knows his median, this is given to us, is 18. So I'm going to draw it here. Next, we draw a box that starts at quartile 1, which is 15 minutes, and ends at quartile 3. Quartile 3 is 22. We're going to draw a box like this. This way to shape that in. What does it say? Kind of interesting. The book says the horizontal lines outside of the box are sometimes called whiskers. Okay? That's your textbook's interpretation. I'm not going to describe them that way. I'm going to say pay attention to what's in the box. In this box plot, what can we interpret out of this?
The average range of times, not a maximum.
Average range of times. What else? Let's look at that example on page 106.
First quarter is quicker than the third quarter.
First quarter is quicker than the third quarter.
Majority of your pieces are moved between 18 and 22 minutes.
Between 18 and 22 minutes. Good, right here. All right, so we know that our range, let's show these values out here. Those were them in our max. We're going to say majority of them fell here. Now, based on what was just said, what type of skewness, how would you describe the skewness or the shape of that data? Flip over to page 110. And let's look at these examples. Next option. All right, here's three shapes, three common shapes in which data can be graphed. What do we call this? Symmetrical. Take an econ, you take any type of statistics, we commonly call this bell-shaped curve. We know a symmetrical curve or symmetrical curve. I can carve it in half, and at the median, it can be split into two equal parts, one on each side. With a symmetrical, I can tell you that the mean and the median are identical. So it's common shape, and the mean and the median are the same. What kind of shape is this?
Hill.
Up the hill, then down the hill. This is positive skewness. And then what do we have here? Negative skewness. So in this case, look, the median would be somewhere around here. And the mean is going to be right of the median. There's more data. Look at this. More data under the curve is out this way. Here, more data is where? The opposite. So the mean is going to be out here to the left. Now go back to this example. If I graph this, I go from 13 to 30. Where is a majority of my data? Which type of description down here would you assign it to? How is this data skewed? Positive. This is a positive skewed box plot. You see that your third quartiles, 3 of these quartiles are all under this range. Then we're going to tell out here to the end.
So the mean means it has more data on the mean does.
Whenever you're looking at the difference between the median and the mean, and what could separate those, go back to the example of the salaries that we threw up there, the power of the outliers, and how if you have one large outlier, how it can drag the median, or excuse me, drag the mean
Right.
out.
Yeah. Gotcha.
All right, the last thing I want to cover is on page 110, several formulas in our statistical textbooks to calculate and quantify skewness. The one we are going to look at is the simplest, developed by Professor Carl Pearson, and it is based on the difference between the mean and the median. So the Pearson coefficient. All right, so the Pearson coefficient let's look at the formula. We denote it with SK. And let's translate this formula. It is 3 multiplied by what?
Or
X bar.
X bar.
Let's put a description behind that. 110. The mean of what? The sample mean minus what? And what are we going to divide by?
Yep.
Now what is, when you calculate this, realize that the coefficient of skewness is going to range between 3 and -3. A coefficient skewness calculated at 3. Interpret it for me. The more I move toward +3, Which way am I moving?
Because I could listen. This is positive, and a number closer down here is going to indicate
Negative skewness. A value of 0 is going to show what?
No.
Even. You would have a symmetrical distribution. So if you wanted to measure the strength of skewness, you would apply Pearson coefficient.
what that problem was. The level is given.
The level, or if you wanted to measure the strength of the skewness, I would apply this formula. Like I say, if you want to quantify, you know, in statistics, it's one thing to look at this and say, this is a positively skewed distribution. There will be times when you'll have to measure how positive is it. You know, and again, if we came up with 0, well, you know, we're going to be symmetrical.
Half now.
Any questions?
When do they use this? What kind of data like?
When would they use this and what kind of data? Well, look on page 111, and it says following are the earnings per share for a sample of 15 software companies. Earnings per share are arranged from smallest to largest. Compute the mean, median, and standard deviation and find the coefficient of skewness. Draw a conclusion. Ladies, we good?
Yes, we're good.